In this video, we're going to prove an important theorem about continuous functions on compact metric spaces. And the theorem is that if you have a function from one metric space to another, so let E and E prime be metric spaces, and you have a continuous function, you have a continuous function from the metric space to the other metric space, and the domain is compact. So f is a continuous function. If E is compact, then f is uniformly continuous. So the proof of this is a bit tricky, and I'm going to give an attempt at a proof, and then we'll see what goes wrong, and then we'll figure out how to fix it. So before we do that, I think it's worth pointing out a little lemma that is useful. So suppose that you have a continuous function. Suppose f is a continuous function between two compact suppose f is a continuous function between two metric spaces. I don't know why I abbreviated this. Then if you have a point P in E, then for every epsilon greater than 0, there is some delta, which depends on P, such that if you have 2 points in the open ball centered at P of radius delta, then the distance between f of q1 and f of q2 is less than epsilon. So this is slightly different than the definition, because the definition of f being continuous at P means that for every epsilon there's a delta, such that if the distance between Q and P is less than delta, then the distance between f of Q and f of P is less than epsilon. And here we have a statement that there is a delta such that whenever you have 2 points in the epsilon, in the delta ball, then the distance between the outputs is less than epsilon. So basically what's going on is you have a point P, and you know that there's some delta such that if you have a point, say Q, then the distance between P and Q is less than delta. If the distance between P and Q is less than delta, then the distance between f of P and f of Q is less than epsilon. That's the definition of being continuous at P. But this statement is applying it to any Q1 and Q2 in this delta ball. So the proof of this lemma is, well, since f is continuous, we know, so let epsilon be greater than 0, we know that since f is continuous, there exists some delta such that if Q is in the ball of radius delta centered at P, then the distance between f of P and f of Q is less than epsilon over 2, right? So now the triangle inequality comes to the rescue. So now let Q1 and Q2 be within delta of P, this delta. Then the distance between f of q1 and f of q2, by the triangle inequality, this is less than or equal to the distance between f of q1 and f of p plus the distance between f of q2 and f of q1. F of p, sorry. Maybe I should just rewrite this to be a bit more clear, right? So this is from the triangle inequality. And then each of these is less than epsilon over 2. So you get epsilon over 2 plus epsilon over 2, and that's epsilon. And that's the proof of the lemma. Okay, so now we will attempt a proof of this theorem that if you have a continuous function on a compact metric space, then the function is uniformly continuous. So here's the attempt at the proof. And the attempt at the proof uses some fairly standard techniques. So let epsilon be greater than 0. Okay. Since f is continuous, we know that for every p and e, there is some delta depending on p, such that for all q1 and q2 in this ball of radius delta centered at p, such that for all q1 and q2, the distance between f of q1 and f of q2 is less than epsilon. That's by the lemma, right? By the lemma, I'm just writing what the lemma says. Okay. And so for every p in your space, so here's a little picture. So suppose that E is like a closed interval in R. So that's E. So you know that for every P, there is some delta of P such that whenever you have 2 points in this open interval, then the distance between F of those points is less than epsilon. So now the obvious thing is to just take the union of those open balls, right? So we have E is the union over all P and E of these open balls. And now we apply the compactness. So since E is compact, we have a finite subcover. So there are P1 to PK in E such that E is the union of these open balls. So we have this equality. And so basically what's going on is you have P1 through PK. Okay, so this is like P1, that's P2, that's P3, let's say that's P4. And basically you have these open neighborhoods of this finite number of PIs, such that whenever you have 2 points that are in the same interval, then the distance of F of those points is less than epsilon. So the natural thing is to choose delta to be the minimum, right? So we apply compactness, we have a finite union of open balls, and we have a finite number of radii, so we can take the minimum. So let delta be the minimum of these radii, So delta of P1 to delta of Pk. And the question is, does it work? So this delta works. Well, let's see if delta actually works. So let P and Q be in E such that the distance between P and Q is less than delta. So we have that E is the union of a finite number of these open balls. So since P is in E, there is some I such that P is in the ball of radius delta of Pi centered at Pi. There's some Pi such that P is in the ball centered at Pi of radius delta of Pi. So you have this finite number of open intervals, and let's say P is, so let's say that P is here, and P is in this interval centered at P2. Like, let's say that this is the open interval centered at P2. It doesn't look centered at P2, just drawing the picture. Now, if Q were in this interval, right? If Q were here, then we'd be done, okay? The problem is that you can always take, the problem is that Q doesn't have to be there. So you could take P to be really close to the edge of this interval. So P might be here. And if you take delta to be the minimum of the radii, you could still take Q to be really close to P, but outside of the interval. So you cannot apply the thing that you want to apply to conclude this, because you need your 2 points to be in the same open ball in order to apply the lemma, right? To apply the conclusion. So if we knew that P and Q were both in one of these open balls, then we'd be fine. The problem is that P and Q don't have to both be in the same open ball. Okay, so the issue is that you cannot guarantee that Q is also in the same open ball that Q is in, that P is in. So that's a problem. That means that the proof doesn't work. Okay, so the reason why the proof doesn't work is because the way we constructed this finite open cover, we cannot guarantee P and Q to be sufficiently close to the PIs. That's the issue. We can get the P close to one of the PIs, okay, but we cannot guarantee that Q must be sufficiently close to that PI. So the trick is, so the trick to get around it is, maybe I shouldn't say trick. The strategy, trick, whatever, is go back to this. You have for all, let's see, where is the open cover? We have this open cover, okay, and we took a finite subcover of the open cover consisting of these balls, these open balls. The trick is don't use this open cover. Instead, what you do is you go back. So here's your E. Let's say this closed interval. So you have, for each P, you have some open neighborhood that satisfies certain conditions that you want, right? Okay? So the trick is, don't use the radius delta of Pi. Instead, take half of the radius. Half of the radius for each of these points. And you will also get a cover of E. And then you use a finite subcover of that. So let's write that down. So the trick is replace each of these delta pi's with delta pi over 2. Okay, so we have, so here's the proof that actually works. So you use the same sentences, as before at the beginning. The trick is we take a delta ball, but of radius delta of pi over 2, delta of p over 2 for each p. So we have E is the union over all p and E of the ball centered at p of radius delta of p over 2. And that's certainly true because we took an open ball centered at each p, so E is the union of this. So now we apply compactness. So by compactness, there is a finite union. So there are P1 to Pk such that E is the union of this finite cover. E is the union of this finite number of balls. So basically what we're doing is we're replacing the green, in this picture, the green open intervals with the blue open intervals, where you just take half of the radius of the green open intervals, right? And then we're taking a finite subcover of that. Now notice that we have more open balls, just a smaller radii. So now we have like P1 up to Pk, where this Pk is not the Pk that we had before, right? So now we have more Pi's. But the point is that we really just want P and Q to be both in one of the green open intervals, or the green open balls. Because if we can get P and Q to both be in the same green open ball, meaning the ball of radius, pi centered at pi of radius delta of pi, then we can get the conclusion we want, right? So that was why we took a smaller radius. And then what is the delta that works? We take delta to be smaller than all of the blue radii. So we take delta to be less than the minimum of delta of P1 over 2 up to delta of Pk over 2. And we claim that this delta works. And I think you can already see why this is true. So the reason is because now we let P and Q be in E with the distance between P and Q less than delta. So we know that E is the union of these blue open balls, so we just say there is some I such that the distance between P and Q is less than delta of Pi over 2. Now the point is that when you take delta to be as we did, when you have P and Q might not be in the same blue open ball, but by the way we chose delta, P and Q must be in the same green open ball, and that's what we wanted. So let's write out the details of that. Also, the distance between Pi and Q. Oh, what am I saying? Yeah, the distance between P and Q is less than... the distance between P and Pi is less than delta of Pi over 2. There we go. Also, the distance between Pi and Q is less than or equal to the distance between Pi and P plus the distance between P and Q by the triangle inequality, and then that's less than or equal to delta over 2, delta of Pi over 2, plus delta, and since delta is less than delta of pi over 2, this sum is less than delta of pi. So what did we show? We showed that P and Q are both within delta of pi of pi. So P and Q are both in the ball centered at pi of radius delta of pi. And now we apply the lemma that we had, right? By construction of delta of pi, the distance between f of p and f of q is less than epsilon. And that completes the proof. So basically, let's just review the proof technique. So first of all, you use the standard attempt, which is to take some nice open ball centered at every single point. You take the union, so you get this infinite union, and then you can take a finite subcover, so it's a finite union of balls. And then you try to use delta to be the minimum of the radii. That's also a very standard technique. But the problem was it doesn't work because you cannot guarantee that P and Q have to both be in the same delta ball. So the trick was to replace those open balls by open balls of half the radius. So you go back to the open infinite cover, you change the radii, and then you take that infinite open cover, and then by compactness you get a finite subcover of that. And then when you do that, and you take delta now to be the minimum of the smaller radii, then it works. Okay, and I mean, you can adjust. It doesn't have to be, of course, delta of pi over 2. You could take delta of pi over 3 or something. The point is to choose delta sufficiently small so that you can actually guarantee that P and Q are both in the open ball of pi of radius delta of pi. The delta of pi that guarantee that whenever you have 2 points in that ball, then the distance between f of p and f of q is less than epsilon.